Okay, now we're going to talk about the second stage of neuroconduction, referred to as depolarization. I mean, I'm making this arbitrary situation of 1, 2, 3. I mean, most times you would just be asked to explain depolarization down the axon of an unmyelinated neuron. It would be a classic exam question in physiology, and just as a hint, that is more than likely going to appear in your exam in the midterm, as will muscle conduction, or one of the three parts of it. So you have been warned. So this second part in this talk, not the second part in the process, so that's just all made up to make it easier by making it into smaller chunks. I'm going to talk about is depolarization and how that works. So we've had our EPSPs in the dendrites. Our positive charge has come in where it was originally negative. That positive charge has moved by cable properties across from the dendrites, across the cell body, and arrived at the axon hillock. Now, as we said in the last one, we have sodium voltage gated channels sitting at the axon hillock. If that is increased to that by increasing positive charge from the dendrites, if it reaches here, the first ones open and sodium comes rushing in. That whole area becomes positive. Now, why is that important? Well, I'm going to change colour slightly because it's all getting a bit messed up. Because just downstream of it, I'm doing this in green. So these green ones here, I did these in red, but I'll be doing them in green. Voltage gated channels for sodium. So if that comes in and creates a big positive charge on the inside, well, just by going from minus to positive, you have depolarized that part of the membrane. You have created a positive where there was originally a negative. Once all the sodium comes in, that actually swings all the way to plus 30 millivolts. That positive charge builds up around the next sodium voltage gated channels in the line, exactly in the same way in your excitation of a muscle cell. The sodium voltage gated channels were stimulated to open by the original opening of the chemically gated nicotinic cholinergic receptors, and those sodium channels took the muscle potential right along the surface of the muscle and down the T-tubules all the way to the point where it opened up calcium voltage gated channels on the sarcoplasmic reticulum. In this case, it's just a straight swap. Down comes the positive charge, these open, in comes sodium, positive charge flipped here, more positive charge builds up. These open, in comes sodium, more positive charge builds up. And the whole process, just like a whole series of dominoes, brings positive charge all the way down the inside. Now, if you remember, if this was a motor neuron, we have our acetylcholine up here, and that positive charge arrives here, and it actually causes calcium voltage gated channels to open there, and that goes through a few stages like commodulin, protein kinases, etc., and that causes the vesicle to merge and the acetylcholine to be released. So all depolarization is the opening of the first sodium voltage gated channel, and that is called reaching threshold. Once you hit 55 millivolts, minus 55 millivolts, because of the positive charge coming into the axon hillock from the rest of the dendrites and cell body, you reach threshold, the sodium voltage gated channels open here, bringing in positive charge, and then you have a domino effect, and that's the action potential of the positive charge appearing down the axon and arriving at the axon terminal. It's an all or nothing. Once the threshold is met, it will go to the end of the axon and carry the signal on to the next stage. That is depolarization. Opening of voltage gated sodium channels at the axon hillock, at meeting threshold, that occurring, and then that sequentially opening voltage gated sodium channels down the axon until the positive signal inside the cell reaches the axon terminal. End of story.